Good day everyone, this is Vlad Kustov again with new video about covariant tensor machine. Today I tell you about how the CTM describes classical momentum. I show you how to describe classical momentum graphically. In addition, I answer the question, what is momentum law conservation? For beginning, I'm searching a structure of momentum vector. It well known a momentum vector consists of a velocity vector and scalar inertial mass, while the scalar inertial mass operates to only a scalar momentum vector. In other words, in the scalar of momentum vector, I can't separate out the scalar components of mass and velocity. I know a direction of momentum has the same direction with the velocity. I want to receive separate components in a graphical reflection. At first, I remember about independent components from the past video. If I have two independent components, then a graphical representation is a perpendicular graphical reflection of linear segment. Length of linear segment is a value of linear scalar function. In that way, I can draw two linear segments. First segment is the velocity vector, and second segment is the inertial mass. While the velocity vector has a direction, and that direction operates for the direction of momentum vector. From the drawing can see an invariant of momentum vector is a square of rectangle. Another side, I know that a vector value is consistent row of numbers or sequence. Now it's sensibly obvious think about a separation velocity and mass quantity in momentum vector. Simple linear reflection of momentum as a vector says about an invariant commonly. Here it's worthwhile to consider the mass is a carrier of velocity invariant in space. Velocity vector carries the mass in space. Here it means Newton's space. Here it's necessary we'll find out for the commutator between velocity and mass. It was known that velocity and mass are linear quantities. Velocity and mass are independent values. Therefore, they connect the only one line. Straight line goes from a starting point to the end point of tact. It's diagonal of rectangle. In the picture it was drawn by red straight line. It isn't completely vector, rather it's semi-functional. Momentum law conservation says about a moving of invariant. It gives understanding how invariant conveys from one point to another. Early defined representation of momentum is showing conservation not only length of momentum vector, but square and mass. I am going to explain by the examples. First example is perfectly elastic impact. One mass m1 has velocity vector v1. T lower index is index moment of time. In the picture it's number in circle. Second mass m2 has zero velocity vector. v2 is equal 0. I built linear representation for momentum vectors. This is one moment of time. It's equal 1 second. In second moment of time, I can build distribution of invariant of momentum. Because I know that velocity v1 is 0, square of momentum goes to inertial mass where it appears by v2. As a result, I will get momentum p2 over index. p1 and p2 have equal invariance. It's from momentum law conservation. Difference is only moment of time. It's worthwhile to consider the transition from one to another happens in infinity moment of time. Its point of transformation or sign of equality. It's good looking from linear representation. Now I have question: how to search transformation graphically? If I knew that happens in infinity moment of time, then the end of moment of inertial mass m1 is the beginning of momentum inertial mass m2. Here I can continue a vector of momentum p1 by convention in dash line. As if it doesn't have transition of invariant between two inertial mass m1 and m2. Inertial mass m2 restricts upper border of momentum p2. Beside on commutator between inertial mass and velocity, I can connect m2 and conditional velocity v1 in this moment of time. This diagonal is speed commutator. It defines a graph-analytical connection between two independent quantities. They are velocity, inertial mass m1 and m2. Then I have received direction of commutator. Commutator of inertial mass is search analogously velocity. Second example is exchange velocities. Analogously earlier describing, I have two inertial mass m1 and m2. In first of moment of time, velocities have invariance v1 and v2, but direction are opposite each other. Here appears question: what are velocity after transformation, or what are velocities in second moment of time? At first I can build linear representation where invariance save and see direction. However, it doesn't give invariant of velocities. From initial condition, I know that inertial mass exchanges by velocities. This process I can divide on two parts and bring the goal to earlier example. For searching, I use graph-analytical method or covariant tensor machine. Now I build momentum p1, t1 and inertial mass m2. Then using infinitesimal principle of moment transformation, I draw conditional momentum p1, t1 in second moment of time, t2. Further, analogously other example, I search velocity v2 and momentum p2. For other inertial mass, operation is the same. Third example is confluence mass. This case tells that two masses have velocities and they have the same direction. In result, it appears sum of inertial mass and common velocity. Here, I don't touch theme about algebra of velocity. In other words, how two velocities add in vector space. This is the question our video in future. Condition has estimated such that transformation between two inertial mass happen. Inertial masses create the squares with velocity v1 and v2. They are momentums p1 and p2 in first moment of time. After transformation, I remember that confluence masses happens in infinitesimal moment of time. Then I can build diagram as a sum of momentums and continue it as conditionally momentums in second moment of time. Here, I don't concern all of cases. They are jet propulsion, angle impact, and others. All of them have a decision like getting early. In the end of my speech, I want to make the conclusions. From analytical representation, don't see how invariant of moments to get from one to another. Here, I have only analytical formula. Covariant tensor machine gives visualization representation about transformation and quantities. In other words, if I describe a situation of things in room by text or drawing, analytical method is a text describing. Covariant tensor machine is a drawing describing. Here I finished my conversation about classical momentum. Thank you for your attention. See my next video about development of covariant tensor machine.